Hello everyone and a very warm welcome to Kognito Key. Today we have an absolutely fascinating explainer lined up for you. We're going to unpack the anatomy of a true technological marvel, the rhombic antenna. If you've ever wondered how engineers manage serious, long-distance radio communication using some of the most structurally impressive designs out there, well, you are exactly in the right place. So let's dive right into this giant diamond in the sky.
So what exactly is a rhombic antenna? At its core, it's essentially what we call a traveling wave radiator. It's built by connecting these incredibly long conducting wires in the distinct shape of a rhombus, basically a giant diamond. Now, this isn't just for aesthetics. It's a highly directional, broadband antenna designed to radiate maximum power perfectly along its main axis. And because of this massive diamond-like structure, it requires a lot of space. That's exactly why you'll see it used in applications where physical placement just isn't an issue. Now, a really crucial point to understand is where this antenna actually operates on the spectrum. The rhombic antenna is specifically engineered for high-frequency and very high-frequency ranges. We're talking right in that sweet spot between 30 and 300 megahertz. It really is an absolute workhorse for these specific broadband frequencies.
Okay, moving on to Section 1, the blueprint, constructing the diamond.
How do we actually build this massive structure horizontally above the ground? Well, constructing this diamond requires 3 precise steps. Step 1, you need 4 conducting wires of absolutely equal length. Step 2 is the feed line excitation. This is where we introduce the power using either 2-wire transmission lines or a coaxial wire. And finally, step 3, and this is incredibly important, the resistor termination. The end opposite to the feed line is capped off with a carefully adjusted load resistance, typically right between 600 and 800 ohms. This specific resistor value prevents standing waves from forming in the legs of the antenna, completely setting up a non-resonant condition.
Let's look at Section 2, the engine, how it works and radiates. Let's break down the physics of how this structure actually moves radio waves. Picture this. When power is provided, current shoots through the legs of the rhombus. Now, in a resistor-terminated setup, the antenna just absorbs that traveling wave right at the end, eliminating reflections. This makes it unidirectional, meaning it radiates perfectly in the forward direction. But if we leave the ends open without a resistor, the waves just reflect right back towards the feed point, creating a bidirectional pattern. Both modes have similar power losses, but capping it with that resistor is what gives us that beautifully focused point-to-point communication. And honestly, this is exactly what you should take away from this. When properly terminated with that 600 to 800 ohm resistor, the unidirectional radiation flawlessly aligns along the main axis of the antenna. It combines perfectly, pushing all of that radio energy exactly where you need it to go.
But, there is a catch, and that brings us to Section 3, the upgrade, boosting power with arrays.
So, here's the thing. A single-wire rhombic antenna has a fairly major flaw when it comes to transmitting. Up to 50% of the power gets completely wasted, just absorbed right up by that terminating resistor. That is a massive amount of lost energy. But engineers, they have a brilliant fix for this. By combining multiple rhombic antennas, either serially or in parallel, into an array setup, they recover that lost power. Radiation efficiency literally skyrockets from a mere 50% to 90% or more. It's a real game changer.
Finally, let's wrap up with Section 4, the verdict, pros, cons, and real-world uses.
So, why do we still rely on this diamond in the sky today? Well, the benefits are super clear. First off, the structure itself is simple and highly cost-affordable to build. Second, it's incredibly directional. Third, both its radiation pattern and its input impedance stay amazingly constant over a really large range of frequencies. You can easily switch working frequencies without changing any of the hardware. And lastly, its low vertical radiation angle makes it absolutely perfect for long-distance F-layer skywave propagation.
But of course, we have to look at the drawbacks too. To use this antenna, you need a tremendous amount of physical land. The installation is just massive. And like we just talked about, the low transmission efficiency of a single wire means you almost always have to build a multi-antenna array to make it truly effective for transmitting.
Tying it all together, the rhombic antenna remains a totally essential tool for high-frequency and very high-frequency point-to-point communication. When you literally need to bounce signals right off the ionosphere for global long-distance communication, this highly directional broadband diamond is exactly what you rely on.
So what do you think? Are you ready to build your own diamond in the sky? I really hope this deep dive brought the science and engineering of the rhombic antenna to life for you today. If you want to keep exploring and learning efficiently with us, please make sure to subscribe to the Kognito Key channel. Hit that like button and definitely share this explainer with your friends and fellow learners. Thank you so much for watching, and I will see you in the next one.